Welcome, aspiring space explorers. Imagine if you could study distant planets, blazing stars, or even the deepest oceans of our own Earth, all without actually touching them. Well, today's explainer is your futuristic mission briefing. We're going to look at exactly how scientists study the cosmos, and more importantly, how you can jumpstart your very own career in space exploration starting tonight, right from your own backyard. So let's dive into this massive mystery. Because, when you really think about it, the distances in space are just staggering. We can't exactly walk up to Mars with a magnifying glass. Scientists had to figure out a literal superpower to see these faraway, untouched worlds without ever leaving Earth or risking a human crew.
Okay, here's our mission briefing for today. We'll be covering Section 1, Seeing the Unseen Cosmos. Section 2, Mapping Planets and Atmospheres. Section 3, Space-Grade Professional Sensors. And finally, Section 4, Your First Space Camera. Let's get right into it.
Section 1. Seeing the Unseen Cosmos, the core science. Let's start with the fundamental science that really acts as the absolute backbone of all space exploration.
The crucial point here is that remote sensing basically acts as a pair of super eyes for scientists. By collecting information from a distance, we're completely bypassing the physical limitations of space travel. So instead of touching a rock on some distant moon, we use these highly specialized sensors. They capture photons of light and literally convert them into data we can analyze. This could be visible light that we can actually see, or completely invisible waves like infrared and radio waves.
Now check out how this slide perfectly contrasts our two primary methods of gathering cosmic intel. Passive sensing is, pretty much exactly what it sounds like. It's waiting and watching. It relies on natural radiation, mostly sunlight, bouncing off an object and hitting our sensors. Active sensing, on the other hand, is when the spacecraft takes charge. It actively shoots out its own signals, like radar or laser system called LiDAR, and then precisely measures what bounces back. It's basically the difference between taking a photo in natural daylight versus using a camera flash in a pitch-black room.
All right, moving to Section 2, Mapping Planets and Atmospheres, Real-World Missions. Let's see how this builds into actual applications across our solar system.
This brilliantly illustrates a miniature narrative of how active and passive sensors work together. It's the anatomy of a rover mission. Before a rover ever touches the dirt, satellites in orbit use passive sensors to map the planetary terrain in high definition. Then, they use that data to pick a safe landing site, completely free of dangerous boulders or craters. Finally, once the rover lands, it uses active sensing systems to navigate safely across the alien surface, pinging the terrain so it doesn't get stuck. It's like a perfect high-tech relay race. And beyond just landing safely, scientists use these sensors for some absolutely vital studies. They analyze alien weather by measuring atmospheric gases. They uncover hidden resources like water ice or precious minerals on the moon, which is insane because we can literally spot a water table from hundreds of miles up. That is a real game changer for future space colonization. But actually, it's not all deep space. We turn these super eyes back on Earth too, tracking climate change, deforestation, and even managing natural disaster responses right here at home.
Okay, Section 3, Space-Grade Professional Sensors, the heavy machinery. Because to execute these incredible feats, we need some of the most advanced hardware ever engineered by humanity.
Just look at this roster of incredibly costly optical gear from leading aerospace companies. You've got massive space reflectors from L3 Harris and Northrop Grumman, and ultra-high-resolution lenses from legendary optics companies like Zeiss, Leica, and Genoptic. Add scanning and steering mirrors from Cambridge Technology, plus specialized diffraction gratings. Every single piece of glass has to be flawless, designed to catch just a few stray photons of light from a galaxy millions of light years away and funnel them perfectly into our sensors.
And once that light and radiation are captured, they hit these specialized electronic components. These are the literal digital retinas of our spacecraft. Companies like Teledyne E2V, Sony, and Hamamatsu build linear CCDs and focal plane arrays that take that gathered light and physically convert those photons into an electrical charge. That tiny electrical spark, that's what translates the universe into digital data. And remember active sensing? We use avalanche photodiodes from Exelitis or First Sensor to detect the absolute faintest laser bounces for LiDAR. They even use these special spectral-on targets from LabSphere just to calibrate the sensors so the data is dead-on accurate.
I love this quote because it really hits the nail on the head. Without this massive investment in cutting-edge optical and electronic gear, we would literally be flying blind in the dark. Instead, they deliver undeniable proof of untouched worlds.
All right, let's pivot. Section 4, your first space camera, the accessible alternative. We're bringing this incredible tech right into your own backyard.
Now, what's absolutely wild about this slide is that the fundamental principles of capturing light are exactly the same, whether you're NASA or a student standing in your driveway. Sure, space-grade sensors cost billions of dollars and use extreme environment CCDs or avalanche photodiodes, while your entry-level mirrorless camera costs a few $100 and uses a consumer CMOS sensor, but at their core, both are doing the exact same science, passively capturing light to convert photons into digital data, revealing things the human eye just cannot see.
So for you aspiring space explorers, you definitely don't need $1 billion to kickstart your remote sensing journey. This simple, accessible gear list is literally everything you need. A basic mirrorless camera body, a couple of lenses, a sturdy tripod to keep it all perfectly still, and a remote shutter release so you don't shake the camera. That's the whole shebang. You are now equipped to be a backyard astronomer. Well, actually, you'll probably also need a heavy winter coat and a lot of coffee, for sure. And this brilliantly illustrates how simply changing your lens lets you hunt for completely different cosmic targets, just like scientists swapping instruments on a satellite. Slap a wide-angle lens on, and you can capture sweeping star fields and the Milky Way. Switch over to a telephoto lens, and you can zoom right in to photograph the moon's rugged craters or even the rings of Saturn using long exposures.
Finally, launch your space career. I want you to see how connected this all really is. Exploring space is no longer just for professionals with massive budgets.
Remote sensing has mapped planets, guided rovers, and uncovered hidden resources across our solar system. Armed with a basic camera, some patience, and the remote sensing principles we've covered in this explainer, you can step into that exact same spirit of exploration tonight. The universe is waiting for you. So, what world will you uncover first?